Hello everyone, myself Yadagiri, Assistant Professor, Department of Electrical and Electronic Engineering and also the Faculty of Basic Electrical Engineering. So in this session, we are going to discuss about the series and parallel connection of the resistors. So in that, first we need to discuss about the series connection. So before going to commencing into the series connection of the resistance, so first of all, we need to aware about the series connection. So series connection nothing but it is an interconnection of the various elements connected with the different points or different ends. So let us say this is the R1, this is the element R1. So it has two terminals. This is the starting end, and other one is the ending end of this one. And also the element number 2. This is the starting end and ending end of this one. And also this is the starting end and ending end of this third element. So this is the connection. We can say it is an interconnection of the different elements with the different points or different ends. So let us say the various elements we need to connect with the hand and leg mode. So this kind of connection is called simply series connection. So by connecting these three elements in the series, so we need to get from this one so the equivalent value. So based on that, we need to find out the equivalent value of the series connection. So for that, let us take a R1, R2 and R3 elements so connected in series, and we need to find out the equivalent of this one. So further, let us apply the Kirchhoff voltage law for this one. So we will get from this one so that is a minus V, means apply the KVL. This is the flow of current through the whole network or whole circuit. This is the I. So the same amount of current is circulating in the entire series circuit because there is no current division taken place. So same amount of current moving towards the each and every element which is given by the source. So for that, apply the Kirchhoff voltage law. So this is the way of current circulation in this network. So for that, the voltage given by the source is a minus V, and the voltage across the first element is, we can say, plus V1, and we can say the plus V2 and plus V3 equal to 0. So according to the Kirchhoff voltage law, so algebraic sum of the voltage drop across the each and every element plus source voltage should be equal to 0. According to that, we got the equation is like this. So then we equal to, so V1 plus V2 plus V3, and need to elaborate the each and every element value, that is in terms of Ohm's law, that is I into R1 plus I into R2 then plus I into R3. So this is the applied voltage. Also we can take the notation as a V total. So here also we need to keep V total, here also V total. Then V total equal to, so we got finally I of, means I is the common for each element, so that I of R1, so plus R2 plus R3. So then also we can replace this V total as I into R total. So then I of R1 plus R2 plus R3. So these two gets cancelled. So this R total we got, R total equal to R1 plus R2 plus R3. So by this one, so we need to get the equivalent value of the three resistors are in series, means three resistors are contained in series. The equivalent value should be R equivalent is the R1 plus R2 plus R3. So that this is the R equivalent. Also we can say R total equal to R1 plus R2 plus R3. Means if you are able to connect the different resistors in series mode, simply we need to add the magnitude of those values. So that is the resultant or equivalent value of that connection. So that is a series connection of the different elements. So this is the three number of resistors are arranged in series. If the n number of resistors are arranged in series, so the effective resistance, means equivalent value of that combination is a R1 plus R2 plus R3 plus so on Rn. So this is the equivalent value of the resistors connected in series, means n number of resistors connected in series. So based on this, the Kirchhoff voltage law only we need to derive this expression. So finally, so we need to conclude the point is, so whatever the elements are connected in series, if we want to get the equivalent of that combination, simply we can add them their magnitude values. So that is the equivalent distance of series connection of the resistors. Now coming to the second one, that is a parallel connection. So parallel nothing but when the different elements are, so this element has a hand terminal and also the leg terminal. So this element is also, we can say, hand terminal and leg terminal, and this one also hand terminal and leg terminal. when the different elements are or different resistors are connected in the same points, I mean same handed leg connection. So hence that connection is simply called as a parallel connection. So other words, also we can say it is an interconnection of the various elements with the same terminals, like first and also the end and end. So starting and also the ending terminals are joined together with a common point. That connection is simply called as a parallel connection. So let us consider here different elements, that is R1, R2 and the different elements, so that we can take here the same circuit as an example. So this is R1 element and this is the R2 element and this is the R3 elements. So these three elements are connected in parallel. So based on this one, how much we got the equivalent resistance value, so that we need to analyze by using this circuit. So for this need to connect one current source to this one. So this is the current source. So the current source is the I total. So the current given by the source is I total and this is the node point, and the current through first resistor is the I1 and this is the I2 and the third one is the I3. Then apply KCL at node point. To get the effective resistance of the above connection, we need to apply the Kirchhoff current law. Then apply KCL at node point. So this is the node point. Then we can apply the Kirchhoff current law here, so that we will get the I total equal to I1 plus I2 plus I3. So based on the at a node point, algebraic sum of the incoming currents are equal to the algebraic sum of the outgoing currents. According to that, we got the expression I total equal to I1 plus I2 plus I3. So I total key capacity is we can replace with the I1 as V by R1. So before going to the these all terms, so there is a hidden voltage source behind the current. There is a hidden voltage behind the current, that is a V total. The same amount of voltage also appear across the first element. This is the V1. Then also the same amount of voltage taken by the second element, that is a V2, and also the same voltage also taken by the third element, that is a V3. So all elements are taken the equal amount of voltage, because there is no the potential drop across the entire line. That's why the same amount of voltage taken by the each and every one. So whatever the source voltage, so given to the voltage, the same amount of voltage, so carried by the each and every element in the parallel connection. Means what I want to say the point means, so in the parallel connection, so there is no voltage drop. I mean there is no voltage drop occur. So whatever the voltage given by the source, the same amount of voltage taken by the each and every element. But there is a division in the current. That's why the current should be divided in the parallel connection and the voltage must be constant. So for that the voltage across, I mean we need to elaborate this expression. The I1 equal to according to Ohm's law, V by R we can write, that is V by R1. Then the I2 is a V by R2, then V by R3. So the total current of the network, we can also replace it as V total upon R total. So which value equal to the then V of 1 by R1 plus 1 by R2 plus 1 by R3. So here this is the total voltage and this voltage are both the same. So here we need to write this expression. This is, we need to say sometimes R 1 by R equivalent, or also we can say 1 by R total equal to, it's a 1 by R1 plus 1 by R2 then plus 1 by R3. So from this one we would like to get the equivalent resistance value. R equivalent equal to the then R 1 by R equivalent equal to the, we can write the R1 into R2 into R3 is the LCM of the denominator, and the remaining terms in the numerator is a R2 into R3 plus, here we got R1 into R3, here R1 into R2. So this is the 1 by R equivalent value. From this one need to get the exact equivalent resistance of this combination. So that we need to write the R equivalent of the, so this kind of circuit is, so it is R1 into R2 into R3 upon R2 R3 plus R1 R2 then R3 into R1. So this is the effective resistance from the parallel connection. the effective resistance value of this kind of parallel connection. So if the n number of resistors are arranged in parallel, then the equivalent resistance value is this one. 1 by R total or 1 by R equivalent should be is a 1 by R1 plus 1 by R2, so on 1 by Rn. So this is the effective resistance of the parallel connection of the resistor. So this is the parallel and series connection. In the parallel connection, so there is no division of the voltage, only current should be divided in terms of I1, I2, etc., I3, up so on In. So in case of the series connection, there is no the division of the current. So whatever the current given by the source, that should be maintained by the same amount to the each and every element, but the voltage must be divided in the series circuit, because there is a potential drop across the each and every element. That's why in the series connection there is a voltage drop occur by the each and every element, but the current must be constant. In case of this one, opposite, means current should be divided and the voltage must be constant. So then coming to the also we need to discuss about the fundamental techniques, that is the principles of the different shortcuts, that is voltage and current division rule. So first we need to discuss about the current division rule. So the current division rule, so wherever the current dividing, so we can apply that rule into that kind of circuits, means the current division happen in the parallel circuits only. That's why the current division rule is applicable for the parallel circuits. So according to this one, we can write the expression as, so this is a given circuit, the circuit, let us say, so this is a circuit. So the same circuit I am going to redraw this one. It is applied voltage, and this is the R1 resistor, and this is the R2 resistor. So the current given by this element is a I total, I am going to say. So this is the R1 and this is the R2, and the current flows to the first element is a I1, and current flows to the second element is a I2, and need to find out the current through each resistor by using this principle, without using any kind of Kirchhoff laws or other Ohm's laws. So directly we go through this the principle or technique, then we'll get the current through each resistor. The current division rule is a technique or principle to determine the current through the each element when they are in parallel. That is the current division rule. So it's purely applicable for parallel circuits only. So according to that, first of all, we need to find out the total current of circuit. We need to apply the KCL at this node, so that we will get I total of circuit equal to, that is I1 plus I2. So this is the equation number 1. So whatever the voltage given by the source, that should be same as each and every element. So that voltage across the R1, voltage across the R1, that is also same as the total voltage, and voltage across the R1 and R2s are the equal. We can simply write V total equal to, then V1 equal to V2. So the voltage across the R1 is a V1, we can say, and the voltage across the R2 is a, here V2 we can write. Then V1 equal to V2 equal to V, we can say, because the voltage should be constant in the parallel connection. So according to this one, we can also write V1 equal to V2, because we have only two elements. So we can elaborate this term with the help of Ohm's law, so that is I1 into R1, then I2 into R2. So this is treated as the equation number 1, it is, and this is the equation number 2. So from the equation number 2, here what I want to deriving means, so how can we get this kind of formulas in the current division rule? So that I am going to deriving here. So based on these formulas only, we can get the current through the individual resistances in the parallel connection. So from the equation number 2, we got the I1 value as I1 equal to I2 into R2 upon R1 we got. So this I1 value substitute in the equation number 1. Here I am going to write. So I1 value substitute in equation number 1, so that we got the I total equal to the I1 as, it's a combination of I2 R2 upon R1, then plus it is a I2 keep as this. Then we need to send this value to the left side, so that we will get I2 of R1 plus R2, the left arm. So which equal to I total into R1 we got finally. So from this one I2 equal to I total into R1 upon R1 plus R2 we got. So means what I want to conclude here means the current through the resistor number 2 value is this value. The current through this value is the total current of circuit into. So the R1 is the opposite of this element. That's why it is, we can say this element is a opposite resistance or opposite element or opposite resistance upon the total resistance. So this current is a total resistance we can write, or we can say total current. So this corresponding element is a opposite element. We can write the opposite element. So this one is the total resistance value. The denominator we can say total resistance value. So the current division rule is clearly saying us the current through the particular element in the parallel network equal to the, here the current through the second element, that is R2 equal to the, so total current of circuit into opposite resistance by total resistance. Here also the current through the second element, so the total current of circuit into opposite resistance upon total resistance. This is the current division rule. So the current division rule, so here we have to use the current division rule in the parallel circuits to determine the current through each resistor. So this is the discussion about the simply current division rule. Now the left thing is the voltage division rule. So the voltage division rule is applicable for series circuits. So it is a technique or principle to apply the series network to determine the voltage across the individual elements without applying the Kirchhoff and also the Ohm's law. So here according to the previous case, according to the current division rule, so here also we need to apply some kind of laws to determine this kind of formulas. So based on that only we can say, so the voltage across the particular element value equal to the total voltage into same distance. Previously we have taken opposite distance. So how can we get this kind of formulas means we can go with the analysis. Now let us consider this kind of simple circuit, then apply some voltage to the simple circuit. So that drives some amount of current is I. Then apply KVL for the circuit to get the loop equation. So that is here this is the minus to plus, and this is the plus to minus, and also here the plus to minus. Then apply KVL. This is the way of current circulating in the loop or circuit, that is I capital. So by that we need to get the loop equation as minus V plus V1 plus V2 equal to 0. Then V equal to I into R1. We have to elaborate this each and every term, plus I into R2. Then I going to get common R1 plus R2 we got. So the response of the circuit according to the Kirchhoff law, that is V by R1 plus R2. This is the equation number 1 we can assume. Then we need to find out the voltage across each resistor. First I am going to take the first resistor. So this is the voltage across the R1 we can write. So the voltage across R1 we have to give the name, we have given the name as a V1 equal to I into R1 according to Ohm's law. So I value you can get it from equation number 1. So the corresponding value of I is a V upon R1 plus R2 into R1, keep as is. The final term voltage across the first resistor value equal to the, it's a V into V mean total voltage into, so resistance is R1. So we have to calculate the voltage across the R1 means that is a R1 only we got here. So means we can say this one is the same resistance value. So divided by this is total resistance. So the voltage across the particular element value or the first element value in the given circuit equal to the, so total voltage of circuit into same resistance. So previously in the current division rule we have considered the opposite resistance. In this case we have considered the same resistance. So here we can write it is a total voltage. It is a total voltage. So this one is a same resistance, and this one is a, so total resistance, same resistance and the total resistance. So this is the voltage division rule the proof, I mean, how can we got this kind of expression means based on this analysis only we got this kind of expression. So according to the voltage division rule, so we need to get the voltage across the first element equal to the, so total voltage of circuit into same resistance upon total resistance. So similarly the second element, that is a voltage across the this element equal to the, so that is the total voltage of the circuit into same resistance upon the total resistance. So this is the voltage division rule. Also written in terms of the equivalent value, the R1 and R2s are equivalent of the above connection, that's we can represent by the R equivalent. So according to that, V1 equal to the, so total voltage of circuit into same resistance upon the equivalent resistance value. So that this is the formulas of the voltage division rule. So both are the, here I am going to conclude the point is both are the fundamental principles to get the voltage and current values of the different circuits. Means by using the current division rule we can get the current individual element current values, so without applying any KCL and also the other Kirchhoff laws. So what about the voltage division rule? It is also a fundamental technique to determine the voltage across the individual resistances when they are in series. So these are the voltage and current division rule.